I'd like to give the podium to Roger Dingledine. He's the project leader of the Tor project and will talk about security analysis of Tor.
Okay, hi everybody. I'm Roger Dingledine, the project leader for the Tor project, and I'm going to tell you a little bit more about ways that people can break Tor at this point, both practical and academic and theoretical. So there are a lot of things we could talk about today. I'm going to give you a crash course overview on Tor for people who don't have a good handle on how it works. And then I've actually skipped over all the stuff that we know how to do because that's not as interesting as the stuff that we don't know how to do. So we're going to spend most of our time on hard problems that are practical issues like application level vulnerabilities. And then we're going to focus on the research questions. There are a lot of people over the past year or two that have been coming up with really great academic research attacks that might be able to break Tor's anonymity. And then we can focus on what we're going to see over the next few years, and hopefully there will be time for some questions. So, big picture, Tor is an anonymity system. The idea is that there are a network of volunteers all around the internet, and they relay traffic for users. So users build a path through the network and connect to some website or IAM server or something like that. And the goal is that somebody watching the local connection can't figure out what website you're going to, and somebody at the website side can't figure out where you're coming from. And ideally, no single place in the middle can learn both where you are and where you're going. So it's free software, open source. You can get it and use it and give it away. It comes with a specification and full documentation of this is exactly how you can build your own Tor. And several different groups in Germany and a fellow at Yale University built their own compatible Tor client. And it turns out that multiple implementations are a really good idea. It also means that a bunch of researchers used to look at the theoretic academic designs in anonymity and say, I bet this defense would work, I bet this attack would work, but then they never really had any way to test it. And now there's an actual Tor system out there, and we tell you exactly how it works, and you can analyze whether we got it right. And a lot of people are now actually trying out their defenses and trying out their attacks on the Tor network. And it turns out that most of the attacks work really well. So I don't know if that's a good result or a bad result, but at least now we can know it. There are about 1,500 relays all around the world relaying, I think it's something like 4 or 5 gigabits per second of traffic on average. So that's something up there with Hotmail and Wikipedia in terms of amount of traffic we push. There are some number of users. It's an anonymity system, so it's a little bit hard to count how many users we have. But I'm thinking a few 100,000, 200,000, 400,000, 100,000, something like that. The rest of you should learn your lesson about cell phones from this fine fellow in the front. So, as of the end of 2006, we're an official 501c3 nonprofit in the US, which means that people can give money to us and get tax deductibility for it. We also, as of next week, we're going to be hiring some more people, which will bring us up to 8 full-time developers, which is crazy talk, but I think we can make a lot of good use out of that. We've got a lot of different people funding us, different groups funding us. We were originally funded by the US Naval Research Lab, and then we were funded by the Electronic Frontier Foundation. So our claim to fame is that we're the only project to be funded both by the US DoD and the EFF for the same free software system. And since then, we've been funded by another US government group called the International Broadcasting Bureau. They're the folks who run Voice of America and Radio Free Cuba and things like that. They have some websites around the world that some people can't reach, and they'd like to fix that. And it turns out once you built an anonymity system, a lot of people use it for circumvention or censorship resistance. They use it to be able to read BBC's website from places where otherwise it would be blocked. Okay, so Who cares about this stuff? When I'm talking to researchers and other academics, I tell them I work on an anonymity system. When I'm talking to my parents and my grandparents, I tell them I'm working on a privacy system. When I'm talking to corporations like eBay and Google and Walmart, I tell them I'm working on communication security or network security, because privacy is stupid, but good point, we do need communication security. And when I'm talking to governments and intelligence groups and law enforcement, I tell them I'm working on traffic analysis resistant communication networks. Because they already have security. They don't need this privacy stuff, and anonymity is scary, but good point, we do need to resist traffic analysis. So part of the challenge of this is figuring out how to talk to all of those different groups and bringing them into the same anonymity set so that they can blend together. Walmart cannot run its own anonymity system and just have Walmart people use it, because then everybody will know who's using the system. So you need all these different groups. And then there's the fourth category that we've been learning a lot more about in the past few years, of people who are behind restricted firewalls, either by governments or corporations or something like that. And now they use the same system for reachability. Now I can reach Voice of America's website, and before I couldn't. How do you build one of these? The easy answer is you put a computer out there somewhere, maybe in San Diego or something, and all the different Alices show up, and Alice 1 says, give me the front page of CNN, and Alice 2 says, give me the front page of Indie Media, and each user asks for something, and then the relay goes and fetches the answer and sends it back. And that works great, except if there's an attacker anywhere in the system. For example, if the relay in the middle is bad, then he gets to watch everything that everybody asks for. Or you can go bribe the janitor at the co-location building, or you can offer money to the CEO and he'll consider his business model. There are all sorts of different ways in which a central point of failure can fail. And you also don't have to actually attack the central point of failure to break in. You can also monitor the network going in and going out. For most of these single hop proxies, it's really just one cable the traffic goes in and out on. So if you can tap that, then you win for the entire network. So our goal is to distribute the trust. We want to have multiple different places that need to collaborate, that need to collude in order to figure out which Alice is talking to which Bob. So the idea is Alice is going to pick 3 hops and then connect to some Bob. And if the first guy is bad, if R1 is trying to figure out who's talking to who, he knows that Alice is using Tor. He just doesn't know where Alice is going, what Alice is doing. And if the last guy is bad, then he knows that somebody is talking to Bob, but he doesn't know who is talking to Bob. And if they're both bad, if R1 and R3 are colluding, then we give up, then we're screwed, because there are enough statistical attacks that you can look at the traffic pattern going into the network and watch the traffic pattern coming out of the network, and you can say, hey, wait, these line up. I'm pretty sure that this Alice is talking to this Bob. And then there's crypto, but I'm going to skip over that for the day. There are a couple of points to point out here. One of them is we use different layers of encryption at every step, which means that if you log the traffic between Alice and R1, and then you wait a few days, and then you try to break into one of them to force them to decrypt the traffic for you, it's too late. They've already thrown away the keys, and there's nothing on the relays. There's nothing on Alice, nothing on R1, nothing on R2 that can let you decrypt it. So you either have to break it right then, or you'll never be able to break the encryption. The other key point to notice on this slide is these white lines going from R3 to the various Bobs, those are not encrypted by Tor. Tor does not magically encrypt the internet. This is a little bit of a tricky thing for a lot of people, because they say, well, I installed a security tool and now I'm secure. And turns out the internet's a little bit more complicated than that. So we'll talk about that a little bit more in a few slides. And there are directory servers. So one of the big questions when you're designing a system like this is, how does Alice learn the set of relays she can use? I mean, that's a great slide I've got right there, and we've got R1 and R2 and R3, but how does Alice learn that these are the relays she should use, and how does she learn their keys and their locations and things like that? So the idea is every server publishes a little summary of these are my keys and my address and which ports are open and my exit policy and so on. And it signs that with its identity key. And then it uploads that to the directory directory authorities. There are 6 of them right now. And then they talk amongst each other and produce a little summary network status consensus, signed by as many of them as are willing to sign it. And then that gets cached on all the other relays, so Alice can go anywhere and she can get something, and if it has enough signatures on it, then she'll believe it. Okay, so that was the crash course on Tor. Hopefully everybody understands exactly how Tor works now, at least enough to make sense of the rest of the talk. So there are a bunch of different issues that we can talk about, and feel free to collect questions, and I'll be around all through the rest of the day to answer more questions. Okay, so last year there was this fellow in Sweden who was really good at manipulating the press. And he went to the press and said, I have an attack on the whole internet. It's great. I can watch everything, but I won't tell you what it is. And all of the press said, oh man, that brilliant Swedish hacker breaks internet. I must write the press article. So they all wrote the article about brilliant Swedish hacker breaks internet, won't say how. And then the next week, he went back to the press and said, I did it by running a Tor exit relay and I just watched all the traffic. Isn't that great? And then the press had already sort of gotten into the position where they had to publish because they'd already written the lead story before and now they had to write the follow-up. So he was pretty good at providing press. I haven't actually heard from him since the Swedish police raided him and took all his stuff and took him away. So I guess there are a couple of lessons here. One of them is generally wiretapping the internet without permission of the people you're wiretapping is against the law in most countries. So if you're planning to be a criminal, ask your lawyer first. I guess another lesson there is if you have an attack on Tor, you should come tell us about it first. I actually haven't heard from him before the Swedish police went and raided his system. I've never heard from him. I have no idea who this person is. So if you have an interesting attack on Tor, we'd love to hear from you. So another lesson is Tor hides your location, but it doesn't magically encrypt the whole internet. If you want SSL, if you want end-to-end encryption, then you should get it. You should use HTTPS, you should use POP-S, something like that. And it's a little bit trickier than that because Tor does protect against somebody watching your local network. If I'm on the DEF CON network or the CCC network, I'm going to use Tor when I'm using my unencrypted connections because, oh man, am I not going to use the network directly when I'm using my unencrypted connections. So it's a trade-off of where you want your attacker to be. And then it gets a little bit more complicated than that. A lot of websites use HTTPS as something that is a premium feature, that most people don't need that. Only the really special people are the ones who care a lot. So I was looking at the Wired article from last year about how all the Tor users are dumb because they don't use the encryption button. Shouldn't they just press the button and then they'll have their encryption? So I looked at Wired's website and they have a little login button at the top and they don't use SSL. They don't even support SSL. So it's a more fundamental issue than users on the internet are dumb and they should just click the button. A lot of places don't even let them do it. So we need to figure out some way to make end-to-end encryption and authentication more pervasive around the internet. What else can we do? We could configure the Tor client so that if you try to make a connection to port 23 or 110 or IMAP or something like that, then it pops up a little warning saying, hey, you just tried to make a connection to a port that is usually associated with an unencrypted or plain text connection. Let me teach you about encryption on the internet. That would work pretty well, I think. I mean, we'd have to figure out exactly how to phrase it because all the Windows users are trained just to click OK until things work. So do we make it actually fail by default? And then all the Windows users say, man, Tor sucks? I don't know the right balance of usability there. And even if we solve that one, what about port 80? Some stuff over port 80 is perfectly fine, but other stuff, I'm going to send my HT auth, I'm going to send various cookies. All of that stuff can be sensitive. Probably it's not encrypted, or at least not enough. So we can't solve this just by looking at ports and saying, I think you're being a bad person now, and I'm not sure if you're being a bad person then. And then there are some other options. Maybe we should educate users about how they need to use encryption on the internet. That trick never works. And there are some, I mean, it would be great to have some actual research on exit traffic properties. There was a group at Rice University and another group at Colorado University who actually ran an exit node, and they collected statistics about what came out of their exit node. And they have some interesting results. The majority of connections on the Tor network is web browsing. The majority of bytes on the Tor network is file sharing. So now we know that we need to do some sort of incentive system or balancing system or something so that the file sharers don't take over the whole network like they have taken over the whole internet. So the Colorado University people in particular, they collected their data set. They had traffic logs of connections that people made out of their exit relay. And then they went to an academic workshop and they said, so we really want to anonymize this and then publish it so that other people can use our data set to do research on. But the problem with that is, so the goal of Tor is, if you don't have traffic at both ends of the circuit, if you can't see Alice's side and Bob's side, then you can't win, because you can never realize that this Alice is talking to this Bob. And the people at Colorado were thinking, all we have is the second half. All we have is the side on Bob. So publishing this can't hurt anything, right? Nobody's ever going to be able to match up an Alice because all we have is the second half of the traffic. Imagine there are 10 research groups out there, and 5 of them log their exit relays for a while, and 5 of them log their entry relays for a while, and they all use that same logic. They all say, well, I only have half the circuit, so there's no problem with me publishing this. That might get real bad. So we convinced them that they shouldn't publish it, but it would be great to have some data sets out there. On the other hand, it's illegal to collect them, depending on which lawyers you talk to. So I don't know what the right balance there is. And then the more fundamental questions: who runs the relays? Last year at CCC, I was talking to the WikiLeaks people, and they said, I know for sure that there's a Tor exit relay in China that's run by the Chinese government that's watching everything. How do they know that? I don't know. Maybe they're just making it up. Maybe they do know it. Probably there are some bad Tor exit relays out there. Probably there are some that are watching the traffic and trying to make use of it somehow. At the very beginning, you had to actually send me mail and say, hey, Roger, I want to run a relay. I'm that guy you met at the conference. You convinced me. Here it is. I set it up. And then I would go look at it and see if it's reachable and manually add it to the list. That scaled even less well than I thought it would. So after about 20 relays, I started getting mail from people in Russia and people in various places in Africa and Europe and South America. And if the goal of the Tor network is to have as diverse a set of relays as we can have, then do I say no to these people? Do I say, no, 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 we only want Tor relays at Harvard and MIT because that's where I know people? That can't provide a very stable community, a very stable network. We need a bunch of relays all over the world in order to decrease the chance that there's an attacker who can see the beginning and the end of your circuit. So at that point, you have to let everybody sign up. So now if you want to run a Tor exit relay, just go configure it and start it, and you'll sign up, and that's that. And we are very open. We have a lot of relays. But then we have the question of how do we design a system so that we can tolerate some small fraction of relays that are trying to track people down. And then it gets even more exciting. What if you end up exiting through somebody in Ohio, for example, who's running Windows on his exit relay, and he's running the latest antivirus gadget on it, so that it intercepts all incoming web pages, and it looks through them, and it finds bad JavaScript, and it takes it out, and so on. So that means that somebody in Germany using Tor is actually getting different results because he's popping out of this Windows system that's changing the pages he gets back. Maybe that's good in most cases. I mean, nobody wants bad JavaScript, right? If somebody takes it out, that's good. On the other hand, there's a group at CMU that studies phishing, and they get the latest phishing websites from CERT on the condition that they only look at them through Tor, because otherwise they'll be revealing to the phishing websites that CERT knows about them. So at that point, they actually do want to see the page that they're seeing. We've talked to the Stop Badware group at Harvard, and we've been talking to Site Advisor. I guess they're called McAfee Site Advisor now. And they really want to actually look at the internet from various places so that nobody can say, oh, it's the Harvard Stop Badware group that's looking at my page. I'm going to give them a good-looking page, and I'm not going to try to infect them. So we actually do want to let people see the pages as they should be. What if your exit relay is in China and you're trying to read BBC? So now this nice person in Ohio is just, reading the internet through Tor, and he tries to go to BBC, and the Chinese government censors him. That's not actually what we had in mind. And it actually gets even more scary than that. What if you happen to pop out of an exit node in China and it's doing an SSL man-in-the-middle attack on you? We actually encountered this. We were, searching through the exit nodes, trying to figure out which ones were doing bad things. And there was an exit relay that was just taking off the SSL certificate and putting on its own self-signed certificate. So you go to eBay or PayPal or whatever, and it gets to read all your encrypted traffic. And we thought, oh my God, there's somebody attacking the Tor network. And then we looked at it some more, and we realized that actually it was the ISP for that guy just attacking all of its customers, because Chinese ISPs do that. So we managed to find a Chinese ISP attacking its customers, and some Tor user in Ohio got attacked by the Chinese government because he happened to pop out of some Chinese exit node that was attacking. What if China gets a copy of a root certificate? Now they can swap out the SSL certificates and put in valid ones, and then they can read everything that goes across their network. That's kind of a scary thought. A couple of years ago, we had another question to try to figure out how we should balance these things. What happens if 10 really fast, really stable Tor relays show up, all from 149.9.something.something? And a lot of people looked at that and said, hey, you're being attacked. These are obviously somebody trying to run a large enough fraction of the Tor network that he can see a lot of traffic. So we said, okay, we should investigate who they are. So we did a who is on their addresses, and it's a little place right outside of Washington, D.C., which made a couple of the paranoid people a little bit concerned. And so then we looked it up, and it was a PSINet address. So we got one of our friends at Cambridge University to give a call to the PSINet people, and he called the Network Operations Center and said, hey, who runs this IP address? We're curious. And the PSINet operations people said, oh, wow, you're right. We don't have that in our database anywhere. I guess that is ours. Good point. Which didn't really help the paranoid people. So we actually tracked it a little bit farther back, and we actually found some people who are part of the security hacker community, and they were just trying to help out. They had an interesting business model, which is we sell co-location service, and it's cheaper if you run an exit relay on the stuff that you buy from us. We'll give you a discount if you run an exit relay. And it hadn't occurred to them that running an exit relay on an IP address just next to itself wasn't actually the best way to provide good anonymity for the Tor network, because they were just adding them all to the same /16 network. So the fix for that, in that case at least, is we actually, now the Tor clients look at the different IP addresses and say, I'm never going to use more than one relay from a given /16 in my circuit. So there are a bunch of relays from 149.9, but we'll use at most one of them when we're connecting. So that means we're never going to have one at the beginning of the circuit and at the end of the circuit. Could you run a bunch of different relays with different IP addresses? Sure. There's a fellow at Georgia Tech who studies botnets, and every time I talk to him, he says, with one command, I can sign up 100,000 Tor exit relays all around the world. What would happen if I do that? And my answer is always, please don't. But I'd like to have a better answer than that. And I don't have a better answer than that. So we had another fix, which is no more than 2 relays per IP address. So you at least have to have a bunch of different IP addresses on the network before you can run a lot of different relays and get believed. But what about different autonomous systems? What about different internet exchanges? What about different countries? How do you measure these things? Because looking at the /16 is not good enough. There are plenty of ISPs that have a lot of different /16s all in the same building. So I don't have a good answer for how the client should automatically recognize that these 2 relays are nearby each other physically or administratively or network-wise or something like that. And I want that ideally to be something that's very efficient, that Alice can compute on her own and predict where her path is going to go for any given selection of relays. Okay, and there are a couple of other issues we can talk about. Yes?
Apparently the sound isn't quite going through the stream, so maybe you can contact the guys there and ask.
Apparently the sound is not going through the stream. Can anybody here do anything about that? Yes, I see a hand and a nod. Okay, sounds good. Keep up the good work. Okay, so there are some other attacks we need to worry about. One of the big ones is the JavaScript refresh attack. So here's the way it works. You go to a website using Tor, and it gives you a page that refreshes every 60 seconds. And so it refreshes over Tor, you're fine, you're anonymous, and then you use Tor button to turn off Tor. So now you're not proxying from your browser through Tor anymore. 60 seconds later, the page reloads again, not using Tor, and then you lose because you just told them your IP address. So there are a bunch more subtle versions of this. You don't need JavaScript. You can do it with CSS. You can do it with some other tags. And then there are cookies and history. And whenever I go to a website, I tell them how many pixels by how many pixels my browser window is. I think in IE, they just tell it by default. And in Firefox, you can use JavaScript to look it up. And then there's which language I prefer to speak and exactly which version of Firefox I have. And here are some authentication things. And most of these are problems when you toggle Tor on and off. So now I'm using Tor and I visit this page and then I turn Tor off. And the next page can go rummage through my history and look at all the pages I've seen before. So the new version of Tor button that Mike Perry put out in July of this year tries to deal with a lot of these things. It actually blocks lookups for history, it blocks cookies, it clears the cache every time you switch back and forth, it makes sure to round the size of your window up to a certain amount. So it tries to tackle most of these. And so we used to say, we recommend Tor button with Tor, and now really it's the only option. You better use Firefox. None of the other browsers have something like Tor button, and you'd better use Tor button. And there's some other bugs in Firefox that we're still working on. One of the big ones is if the website you go to tries hard enough, it can figure out what your time zone is, because we can't figure out a way to actually hook the date and time zone stuff inside Firefox in a way that the website can't figure them out. And then another fun one, if you have any client-side SSL certificates, most people don't, then your browser will happily send them to whatever website claims to look a little bit like the certificate. So you can start giving away personal information without realizing you were doing that. And then the other fun one in Firefox 2, when you're doing an SSL handshake, when you're doing a TLS connection, part of the spec says write the current time in this field when you're communicating back and forth. And the Firefox people looked at that and said, we're going to put uptime. We're going to put your computer's uptime in the time field. What the heck? But they did it, and then we went to them and said, shouldn't you fix this? And they said, it takes so much CPU time to figure out what time it is. It's just easier to put the uptime there. And we said, but it's a privacy problem. You should fix it. And they said, there are lots of privacy problems. Why should we fix this one? And that's not good. So I think that they're doing better in Firefox 3, so I guess we just wait. And tomorrow they'll put out another version of Firefox 2, and then maybe they'll end of life it. And then some other problems. A lot of applications are bad at obeying their proxy settings. So PDF is a good example of this. The way it works is you go and you click on a PDF URL, and your browser says, oh, I have a plugin for that. I'll just hand that URL to the PDF plugin. And the PDF plugin gets the URL and says, oh, a PDF, I think I'll load it. And it goes to the network and fetches it. And it's never heard of proxy settings. Why would it use a proxy setting? And that means that if you click on a PDF when you're using Tor, then you just bypass Tor and you go directly to the site. That isn't actually what we had in mind. And then there are a bunch of other plugins. Flash is a good one. Flash can just look up your IP address. It gets to look around locally, it can load files, it can do whatever it wants to do. So Tor is doing its job. Tor is anonymously fetching the Flash applet from the website. Tor is anonymously sending back your IP address. Tor is doing what it's supposed to do. But that isn't actually what people had in mind. So the approach that Tor Button has right now is no plugins. We don't let you use Flash, we don't let you use Java, we don't let you use all the rest of the stuff. And then there are some other tricky ones. Apparently if you put enough backslashes in front of something in Windows, then it turns into a network lookup. That's not good. So there are a couple of solutions here. One of them, and it's a problem because a lot of people do want their Flash. I mean, we're working with the Voice of America people, and they're an actual news organization, and they have to provide YouTube things because nobody else, I mean, nobody wants to read text anymore. They all want to watch little video stuff. So if we're trying to provide circumvention around firewalls, we have to let them watch their YouTube or they get upset. So how do we actually fix this? Turns out it's easy on every operating system other than Windows. So it's a one-liner in IP tables or PF. You just say, all the stuff that's going to go out as TCP, send it to this port instead. And then there's an easy system call, and you say, that connection you just gave me, what was its destination really? And then you just swap it in, and you make your connection, and you're all done. Windows is a little bit messier, but we've got a couple of solutions we're working on. One of them is put a Tor client inside and a Linux kernel inside a QEMU and run that on Windows and intercept all the outgoing connections. So we actually have Linux with IP tables and the system call we want and so on, and it just intercepts all outgoing TCP and shoves it into the Linux plus Tor. And then it turns out it's even faster because Tor performs better on Linux in QEMU than it does in Windows. But I'd like to fix that at some point also. So there's another approach, which is let's put more stuff inside the QEMU. Let's put our Linux kernel, and let's put the Tor client, and let's put Firefox and Pigeon and a few other things, and get them configured correctly. And then people just click, click, and it pops up and it has everything they need to have secured and configured, and it makes sure that all the packets go the right way, and when you close it, it just goes away. So the middle one, the one we're working on is called Tor VM. The bottom one, there's a live CD called Incognito that you can boot inside QEMU, inside Windows, and you've got your whole live CD with all the applications configured right. Okay, so what are some other challenges that we have to tackle? One of the big other ones, I was talking about circumvention or censorship resistance. There are a bunch of different ways that you could block the Tor network, that you could block connections to the Tor network if you wanted to. One of the easy ones, there are 6 directory authorities that I talked about at the beginning of the talk. Their IP addresses and their keys are hard-coded in Tor. So you just go look up those 6 IP addresses, you put them in your national filter, and you're done. No more Tor for your citizens. And if that doesn't work, go fetch the whole directory, and there are 1,500 IP addresses in there, and just put all 1,500 into your network filter, and now you're done. Another option is if you can figure out that the encrypted connection you're seeing is a Tor connection, then you just hang up on it. You say, that's not really SSL, that's a Tor connection. We've mostly fixed that one at this point, but there's still an arms race. We're trying to look a lot like Firefox talking to Apache, because hopefully there are a lot of Firefoxes in the world and a lot of Apaches in the world, even inside and across the Chinese firewall. And then the fourth approach is just block the website and then hope that all the people inside your country say, well, shucks, that was good while it lasted, but I guess Tor's gone too. So The design we've been working on, and I talked a lot more about it here 2 years ago, is a system called bridge relays. So the idea is, rather than having just those 1,500 relays that you can choose from, instead, for your first hop, give all the different Tor users an option to say, I want to be a relay, but not in the public list. Don't put me in the big list of 1,500. Put me in some separate list that you don't give out all the addresses for. So now we've changed the problem from how do we keep 1,500 public IP addresses out of the hands of the Chinese government, which is an impossible problem, to how do we collect 10,000 or 30,000 bridge relay IP addresses from Tor users who want to help out. How do we collect those 20,000 and give them out one at a time to the good guys without letting the bad guys learn all of them? And that's still a tough problem, but it's a little bit of a more straightforward arms race. And I'd be happy to chat with you more afterwards about how that works. Okay, so those were some of the practical issues. I'm a little over halfway done, is that true? Time-wise? I think so. Okay, so there are a bunch of academic research things we should talk about also. Here are a bunch of different ways that you can break Tor, depending on what level of abilities you have and where in the network you can look and stuff like that. The most straightforward one is traffic confirmation. I talked about that at the beginning. If you can watch Alice's connection or the connection at the first relay, and you can watch Bob's connection, or the connection at the last relay, then you can do some very simple math and start saying, hey, I bet these line up. And there are some research designs for how to defend against this. There's one called defensive dropping in 2004, where you send a bunch of extra packets, and then they disappear somewhere along the path. So the set of traffic going in looks quite different from the set of traffic coming out, because not all of the traffic makes it to the end of the network. A lot of it gets dropped partway through. Another design is adaptive padding that came out a few years ago from a fellow who's now at UTexas. And the idea there is to look for gaps and try to fill them in. And that way it'll be a little bit more uniform and a little bit harder to figure out which incoming flow matches which outgoing flow. Unfortunately, the attacks in this arena are usually a lot more effective than the defenses. There was a fellow named Stephen Murdoch, who's actually a Tor developer. A year or so ago, he published a paper at the Privacy Enhancing Technologies Symposium on how do I just do sampled traffic analysis. Let's imagine I'm an internet exchange. Let's imagine I can only see a very small fraction of the packets, 1 in 1,000, 1 in 2,000. And even if that's all I get to see, here is the math that lets me line up which incoming flow matches which outgoing flow. So if you drop more than 99% of the packets, I can still figure out which one coming in matches which one going out. That sucks. So I'm not really very optimistic about fixing this, which means that the way we defend against this, the only way Tor can defend against this, is to grow a large enough network and a diverse enough network that not very many people can see the traffic on this end and the traffic on this end. If you have a better answer, I'd love to chat with you. Another fine attack, website fingerprinting. So there are a bunch of papers in academic conferences saying, if I get to see an SSL encrypted link, if I get to see you doing a connection to some website using SSL, I can guess just by the timing of the packets and how many bytes there are, which website you're looking up. The way it works is I make a list of 1,000 websites I think you're going to, and then I look at the bytes I see on the network and I try to match them up to which website it is. So that means, first of all, I can get a good guess about where you are going, and second of all, I can narrow out a lot of places that you might be going to. Does this attack work on Tor? I have no idea. I've talked to a lot of researchers who say, oh yeah, I started doing the research paper on it and I set up the attack and I tried it and, you know, I'm not really sure if it worked. And nobody really says, no, it doesn't work, and nobody really says, yes, it does work. So part of the reason why it wouldn't work is Tor blocks the bytes that it sends back and forth into groups of 512 bytes called cells. So the fact that we're chunking things up into groups of 512 bytes confuses the attack. Surely the attack will still work, it's just that nobody who's tried has actually made it work. So that's kind of bad, but Not really bad, but maybe it is bad. I don't know. And you can actually probably do a more effective version of the attack by looking not just at, I think this is the front page you looked at, but build a map of the front page of each of these websites and the most popular second links. So now if I see you do some anonymous lookup, and then I see you do a second anonymous lookup, I should say which websites match both of these page loads. And at that point, I should be able to narrow it down a lot faster. Another messy attack that we're still trying to grapple with, called the clogging or congestion attack. So in 2005, Stephen Murdoch and George Danizis published a paper on a low-cost traffic analysis of Tor. And the idea was, there were only 15 relays at the time, so it was a bit easier. You build a circuit from you to each relay and back. So you have 15 circuits, and you're sending constant rate traffic down all of them. And then when Alice goes to the website and fetches a page, you run the website. So you dump as large a page on her as you can, and it produces a big bump in 3 of the relays as it's going back to Alice. And then you watch all of the different constant rate circuits you've got, and 3 of them slow down. 3 of them get congested because there's other stuff trying to go through those relays, and then you know these are the 3 relays that Alice used. So it doesn't actually break Tor, because the goal of Tor is to prevent somebody from learning that Alice is talking to Bob. And all this attack does is let you learn that somebody is talking to Bob, and here are the 3 relays that she used. So the only missing thing is, where's Alice? Which Alice is it? It's a little bit of a concerning attack, because you're basically bridging the entire Tor network, and all of that distributed trust stuff I talked about at the beginning you can ignore. But it doesn't totally break Tor. But it gets worse. There was a paper in 2007 from Nick Hopper at University of Minnesota who said, okay, step 1, do that attack. Figure out the 3 relays that Alice is using. And then I'm going to build my own circuit through those same 3 relays to the same website. And then I'm going to add up the latencies I'm seeing. I know the latency from me to the entry node. I know the latency from the entry node to the website. So I'm going to do a bit of math, and I end up with the latency from Alice to the entry node. I don't know where Alice is, but I know that she's 75 milliseconds from the entry node. And there are a lot of places that are 75 milliseconds from some place on the internet. So if it's some sort of linkable connection, like you log into Wikipedia, Alice is logging into Wikipedia, every time Alice logs into Wikipedia, you do this attack again. And then you start saying, I don't know where Alice is, but she's 75 milliseconds from here, she's 140 milliseconds from here, and she's 20 milliseconds from here. So then the question is, you consult your handy internet latency routing map, which does not exist, and figure out where she is. You just look her up. Can somebody make one of these handy internet latency routing maps? Probably. Can they do it with enough precision that we can actually say, I bet she's in the Ukraine, I bet she's on the east coast of the US? I have no idea. And then there was a paper just this year by some fellows at Columbia on using bandwidth measurements to do the same sort of attack. So step 1, do the 2005 attack. Figure out what the relays are. And then go to the first relay, and they have a way called a packet train measurement that lets you figure out how much bandwidth there is at any given remote point on the internet. The way it works basically is you dump a bunch of packets on it, and you figure out the timing of bounces coming back. So at that point, they can say, I'm able to detect network flows remotely. So then they consult their handy internet routing map, which doesn't really exist, and then they figure out these are the physical connections from the entry node going back. I'm going to measure each one of them and figure out where the flow is. And once I've gone one hop back on the network, I'm going to do it again. I'm going to figure out the physical connections there. And there are, on average, 15 hops from the entry relay to Alice. So I'm just going to hop back 1 step at a time until I get to Alice. Does it work? There isn't really an internet routing map like that. And they need a 30 kilobyte per second flow sustained for 10 minutes to do the attack. But it's not really clear why they need that. Maybe the attack could get better, and then they'd be even better at figuring it out. So they didn't really break Tor yet, but that makes me kind of concerned. And I'm not really sure how to address that sort of attack, because as you're walking your way closer to Alice, you're getting more information about her. And even if we move the circuit away 10 minutes later, sure, you got somewhat closer to Alice, but you didn't quite get there. But the next time you see Alice log into Wikipedia, you can just start up where you left off and say, I'm pretty sure that this one is going to be the flow, and you just keep walking farther back. So does it work? I don't know. And then there's another paper that should be coming out next year, I hope, by Christian Grotoff and some other people at Denver University. They actually tried to reproduce the original attack, the one where you do the congestion attack and figure out the relays. And they couldn't do it, because when that attack was tried, there were 15 relays and pretty much no users. And now when there are 1,500 relays and a lot of users, there are two problems. One of them is it costs too much bandwidth to actually make a circuit through all 1,500 relays at once. And the other one is there are so many users, there's so much noise, there's so much stuff going back and forth that you can't detect when the congestion is happening, when the clogging is happening. So you can't recognize which relays are being used by Alice. So that's great, that's good news. That means that the original attack doesn't work anymore. So these other attacks, the 2007 and 2008 attacks, which started with first do that attack, now they're not reasonable anymore because that attack doesn't work. Unfortunately, then Christian went on to make the attack work again. And the way it works is, so in Tor, you can build your circuit one hop at a time. So you just say, now I have a 2-hop circuit, I'd like to extend this to a 3rd hop. And his approach is, I'd like to extend this to a 4th hop, and a 5th hop, and a 6th hop, and a 45th hop. So he builds this circuit that just goes all around the network. And Tor doesn't really know how to tell if somebody's doing that, because it just sees one hop at a time, and it just knows that somebody's sending packets back and forth. So first of all, this is a denial of service. It's a bandwidth magnification or amplification attack. The idea is that I send one cell, and I end up with 45 cells on the network. So with a cable modem, I can knock over a university-level Tor relay. But then it gets more exciting. Now I can build a loop with my circuit. Rather than just choosing arbitrary places, I choose the same 2 or 3 relays, and I just beat them up. I build my circuit over and over in a triangle. And that means that I can produce enough congestion that I can do this 2005 attack again. I can beat up those relays so much that now I'm able to detect if they're the ones that Alice is using or not. So the attack might work again. Pardon? Okay. So we fixed it. We made it so that Tor can tell if you're trying to build a path that's too long, and it cuts you off after 8 hops. So now the attack doesn't work anymore. But actually, then they fixed their attack. So the new version is you build your 7 or 8 hop path, which is all Tor lets you do, and then you exit from the Tor network to a Tor entry node. And then you run Tor inside Tor, and you build another 7 hops. And then you exit from that to another entry node. And then you run Tor inside Tor inside Tor, and you build another 7 hops. And I don't have a good fix for that. So, yeah, we'll see how that one goes. So one answer is don't have Tor connect to each other. That works okay, except there are these things called open proxies, and you could just get a big list of them and use a new one as glue in between each circuit. There are also these things called bridge relays that I showed a few slides ago. We're intentionally trying to build a list of Tor relays that nobody knows the whole list of. So you should just get yourself a bridge relay and use that as glue in between each of these 7-hop circuits you're making. Then you can start looking at timing, and you can start saying, well, it took him a long time to extend that next hop, so come on, nobody takes that long, except somebody on a modem in Sudan who really does want to use Tor. So I don't have a good handle on that one. Another issue to worry about, and I'm running low on time, so I'll talk about it very briefly. So the question is, Tor changes its circuit every 10 minutes. And the reason for that is we don't want to put too many different web requests on the same circuit. Because when you use that circuit, you say, show me the front page of CNN, show me the page on astrophysics on Wikipedia, here's my Gmail login, and pretty quickly you're going to have said something that can identify you, and then all the other connections you made on that circuit are also identified to you. So the research question is, given a set of web requests that Alice wants to do, how do we allocate them over different circuits so that they're all separate, but we don't build too many circuits? And then another attack we need to worry about. Let's imagine, so Tor's directory system keeps you from spoofing the entire network. You can't lie about which relay you are because you're not going to have the private keys for the right relay. But let's say you connect to the first hop, and you say, please extend this to the second hop, and he says, oh, no, that guy's down. I can't reach him. And you say, okay, well, extend this to this hop then. And he says, oh, he's down too. After a while, you eventually pick one, and they say, oh, yeah, that guy works great. Here it is. You establish your next hop. So the attacker, and this works on the local network also, the local network can say, that node you can't reach, that node you can't reach, that node you can reach. Oh, yeah, you can reach that one. So this means that a local attacker can decide which relays you get to use. And how do we detect this? How do we automatically realize that the attack is going on? Because there are a lot of other options. Maybe your network is down. Maybe you're in a really heavily firewalled place. Do we pop up a little warning in the GUI that says, warning, you might be being attacked, or maybe your network's down, or maybe you're in a restricted firewall place, or maybe you've got a slow connection, click OK. I don't have a better answer than that. Okay, so what's going to happen down the road? Traffic correlation is just going to get better. I can imagine some pretty innocuous sounding things. Let's say somebody publishes an MRTG graph of their relay. So now we have a very coarse graph of how much bandwidth it uses. And let's say somebody else publishes one too. Is the math good enough and efficient enough to take those two graphs and match them up? That would suck, because a lot of ISPs publish that sort of thing too. So how good can we make these correlation attacks? A bunch of more people, more countries, more companies are probably going to start blocking the Tor network. China blocked the Tor website during the Olympics, and they probably are never going to unblock it. So the arms race for Tor bridges is going to start at some point, hopefully not for a while yet. Nobody has blocked the Tor network right now. There are no countries where Tor does not work. And then there's data retention. Nobody really knows quite what the law that you guys have means. The summary, as I understand it, is that service providers, whatever that means, have to log stuff, whatever that means. I've heard from one person who says it means that major ISPs need to remember the IP address that they gave their customers. Okay, that doesn't sound so bad. I've heard from some other people that every person who has a computer has to write down every TCP header for every packet they see forever. That sounds pretty bad. Where's the balance? So the German Privacy Foundation people have talked to a lawyer, and the lawyer gave them a legal opinion that said, it says here service provider, and it actually says service provider who's making money. So if you're not making money, then you're not a service provider, so you don't have to log. That would be nice. I hear that Fobud has put in a claim against the Constitutional Court to try to say that this is a crazy law and it doesn't actually match any of the other laws that we should have, and you should throw it out. They're actually holding a workshop right after this downstairs in workshop room A03 to discuss it a lot more. So if you're a German relay operator, or you'd like to be one, or you have ever thought of being one, or you're not in Germany but you're interested, you should go to room A03 after this and learn more. So I actually talked to a bunch of police in Stuttgart last year after Congress. I flew down there and gave a talk to about 40 detectives and law enforcement officers to try to teach them how Tor works and how internet crime works, and get them up to speed on technology. And one of the interesting things that they told me, I was talking to them about this data retention law and what does it mean and why does it exist and what are you planning to do with it. And they said, we didn't ask for that law. we went to the legislators and we said, can you get the ISPs to answer their mail? Because they don't answer their mail right now. And ideally, can you get the ISPs to answer their mail on weekends too? That's what they asked for. And boy, did they not get that law. They got something very different. And they don't want the law that they got, or at least the people I talked to didn't want it, but they really do want the ISPs to answer their mail, ideally on weekends too. So they're not going to argue against the law. They need something. So they basically told me that they're relying on CCC and FOBUD and other groups to make the law go away because politically they can't argue against it. So that's an interesting approach. So there are a couple of modifications we can do. If it turns out that data retention means that ISPs remember TCP headers, and I'm pretty sure it doesn't mean that yet, so let's not get ahead of ourselves. But if you guys are crazy enough to pass another law in a few years that says everybody must write down everything they see on the internet, we have a couple of design modifications on Tor that should make it a little bit more robust against that. The first one is you never have an entry node inside Germany. And that means that everybody who's using Tor from outside Germany is never going to be noticeable by a German ISP. Nobody's ever going to see that first hop. And everybody who's using Tor inside Germany is going to go outside first, so they're never going to interact with a known Tor server first. And if they want to be really paranoid, they should use bridges, and that way they never interact with anything that people are able to keep track of. We don't need to go that far yet, but we'll see. Another key point, we're not going to put logging into Tor. There are a lot of people who come up to me and say, I really want to obey what I think the new German law means. Can you please put a backdoor in my software? I want to help out. We're never going to put logging into Tor. And the other point, is CCC is going to challenge this law also. They've been talking to various lawyers about the most effective way to do this. And we've been chatting with them also. And the CCC Tor bank account that I talked about last year and that you can find on our donate page and you can find on all of these fine flyers that you have outside, we're going to put all the money that's gone into that account over the past year towards their legal fees for finding a good lawyer and taking down the law. So if you want to put in more money over the next while, it will be put to good use. Okay, so a couple of last thoughts. One of them, pretty much any bug that we find, any sort of, I think this is a denial of service, I think this might be a problem, could be a crash bug, pretty much all of them turn into anonymity problems if you're creative enough. So one of the challenges here is that every time we slip up in any way, if we think hard enough, we can say, hey, couldn't you break anonymity with that too? So it's tricky to do any sort of design modifications because you have to think about all the different issues. Another point, a lot of the hard problems that I've been talking about today, the congestion attacks and the latency and stuff like that, those apply to all the other systems out there also. So I'm not saying Tor is broken by these attacks, go use something else. I'm saying low latency anonymity attacks are potentially broken by these attacks. Consider the attacks if you really need low latency anonymity systems. It's a little bit tricky because when Tor starts, we have a little warning that pops up saying, this is still experimental software, don't use it if you really need good anonymity. And I still have a journalist every few months who writes up a little article saying, the Tor developers don't think Tor is ready for prime time yet. They recommend you use something else for now. No, we don't recommend you use something else for now. Tor is the best that we know about, but it's still not good enough. And then the last point, people find these things because we have a specification, because we are open and thorough and try to explain everything. That's why we have to show up and say, here are all the attacks we know about. First of all, you should know about them. And second of all, please help us fix them. And hopefully, we'd love to hear from you if you have any more attacks or defenses, or you find any problems with Tor. Every so often, there's a new group that puts out a new project based on Tor, and they never think to send us mail first. And that means that we don't ever see it until it goes out, and then we send them mail and say, hey, I think you have a huge security problem right here. And if they're good people, then they say, oh man, you're right, I should fix it. And if they're bad people, they say, well, we already have a lot of money invested in this, and security doesn't matter that much, so we're just going to keep doing it. So we'd love to hear from you before you make that sort of mistake. So thank you.
We have 2 minutes for a question. Yeah? Can the mic go?
Okay. So I've got one good and one bad news for you. One of them is the network map you talked about. Well, it actually does exist. It's something that moves around, so it's dynamic, but it does exist. I've got a researcher just next door my office who's doing this. And the good news is that you can actually use the same technique that phishers or malicious people use to hide their servers behind fast foxing. I don't know if you've heard about it.
Yep.
Well, you could use that to do the Alice and to actually browse people behind blocked countries to Alice, and Alice would be a fast fluxed. Ooh, this is a big difficult word to pronounce. Anyway, so would be fast fluxed through to the Tor network, and this network mapping actually works so well that what we are doing at the moment is trying to figure out the servers of the malicious people, I would say, through actually using many nodes, directing traffic through these flux clients that are actually clients that have been infected with viruses, and monitoring the distance by, of course, measuring the time it takes to travel through the internet, and therefore mapping them on the map of the map of the internet, which doesn't exist. Or
sounds promising. You should chat with me more afterwards.
All right.
I have a remark concerning the correlation attacks. I think adding data to the stream isn't a solution, because you can simply use statistical methods like partial correlation to calculate this out of the data. And so you have the original data back, which you can correlate to the data of the exit point. Should be very easy.
I am not optimistic about fixing traffic confirmation. There are a bunch of different ways to attack it. There are still people who are producing research results that try to show that it slows down a little bit. I'd love to have some sort of result where I can show you, for this level of defense, this is how hard the attack becomes. Some sort of graph that I don't even know if it goes up or if it just stays flat or what. So it would be great to have some results somewhere in there.
Thank you. Thank you for the talk.
Thank you. I will be outside if you have any more questions, and I'm easy to spot throughout the rest of the day, so I'd love to chat with you more. We also have a huge pile of flyers up here. If you know anybody else in your country or around the world who speaks German who needs to learn about this stuff, come grab a big handful and bring them back to your university, city, group, whatever. Thank you.